This is an introduction to section 16.8. Previously, we looked at relative motion for 2 points A and B, which were on the same rigid body. Now we're going to look at relative motion for 2 points which are not necessarily on the same body. So if you go back to section 16.7, we had A and we had point B on the same body, and we were treating this as B rotating about point A, but point A could also be moving through space. But actually, let's go back to 16.5 when we were looking at velocity. So we had the velocity of B with respect to A, and we said that those points A and B, because they're on the same rigid body, the distance between the points isn't changing, so we could just treat that relative velocity between points A and B as an angular velocity crossed with a position vector. Now, the distance between point A and point B can change, and so we're going to have, similarly to what we had in equation 1616, an angular velocity crossed with a position vector, but now the distance between points A and B can also change. So that's what this term here is doing for us. Now, in equation 1616, I had lowercase omega, which was the angular velocity of the rigid body. Here, instead of talking about the angular velocity of a rigid body, I am talking about the angular velocity of a coordinate system. So I have here a coordinate system using a capital X and a capital Y. That's my fixed coordinate system. And then I have a coordinate system with a lowercase x and a lowercase y. That is a rotating coordinate system, and the angular velocity is a capital omega. Now you could choose the rotating coordinate system so that your capital omega for the coordinate system would be the same thing as the lowercase omega for the rigid body. So you could choose it so those are the same. Okay, so I want you to read through the derivation for the equation 1626. And remember, when you take derivatives, if your coordinate system is changing, you have to take the derivative of the unit vectors as well. So that's here, and they walk you through that on the bottom of page 390, so you can read through that, and that's going to give you equation 1626. So this is similar to equation 1616. Here we have the velocity of point B, which we're looking for, is equal to the velocity of point A plus an angular velocity crossed with a position vector. So that's the same thing that we had here. If your angular velocity for the rigid body is the same as the angular velocity of the lowercase xyz reference frame, then it's the same equation if this velocity of B with respect to A is 0. In this section, you can have the distance between points B and A changing, so this does not have to be 0 now. And this is the velocity of B with respect to A as measured by an observer attached to the rotating reference frame. So let's go back here. If you're an observer attached to the rotating reference frame, let's put you at point A. And let's say your rotating reference frame is a merry-go-round, and point A is the center of the merry-go-round. Now, point A can actually be moving, so maybe it's a merry-go-round which is on a train. So you have this point moving because the train is moving, but the whole platform for the merry-go-round is rotating around this point. Now, you are measuring the velocity of point B. You are the observer who is measuring this, so you're not concerned with the motion of the train because you're moving with the train, but you are concerned with how B is moving relative to you. But you are rotating with the platform. So if B is standing still on the platform of the merry-go-round and you are standing still at the origin, you would say the velocity of B with respect to A is 0. So you're both rotating with the merry-go-round, but B is standing still on the merry-go-round, so this relative velocity is 0. Now, if someone was looking and standing on the ground, looking at what was going on, they would say B is moving because the whole merry-go-round is moving. But you, as an observer on the merry-go-round, would say this velocity is 0. This velocity is not 0 if B starts walking around on the merry-go-round. So then you have a relative velocity here, but this is measured by an observer on the rotating reference frame. So this is how B is moving relative to the merry-go-round. The little XYZ here tells you that it's an observer attached to the rotating XYZ reference frame who is making this measurement. But it doesn't tell you that you have to express that vector in terms of, for the little XYZ reference frame, we would use I hat and J hat, little I hat and little J hat. For the capital X, Y coordinate system, you have a capital I and a capital J for your unit vectors. You can represent that vector here using any coordinate system that you want. The little XYZ just tells you who is measuring that velocity. So it may help you to think of it this way. This vector you can draw in a picture, just like we drew the position vectors here. It has a magnitude and a direction. Once you draw the magnitude and direction of that vector, you can then express that vector using any coordinate system that you want. It's still the same vector, so if you draw the vector, it still has the same magnitude and points in the same direction. Let's do an example of this. So let's say the relative velocity is pointed like this. This is the velocity of B with respect to A as measured by someone in the rotating reference frame. Okay, now I can write this vector using whatever coordinate system I want. Let's say this vector has a magnitude of 5. And let's say my lowercase x, y, z reference frame is pointed like this. So this is x, and this is y. Then I could say v, b, a, x, y, z. This vector has a length of 5 and is pointed in the negative x direction. So that would be negative 5 I hat. But maybe I don't want to use that coordinate system. So if I want to use a different coordinate system, and let me try and do it like this. If this is a length of 5, let's make this side 4 and this side 3. It doesn't really look like it's to scale, but oh well. Okay, and we'll make this the capital X direction and this the capital Y direction. I can write this vector using this coordinate system and that would be negative 3I minus 4J. So it's the same vector. If you have this coordinate system, you can draw the vector using this. If you're using the lowercase coordinate system, you would draw the same vector. So it's just being expressed different ways, but it's still the same vector. So the little xyz is not telling you what coordinate system you have to use. It's just telling you who is measuring that velocity. So you have to think This is being measured by an observer in the rotating reference frame that gives you this vector here. But if you want to write it using the coordinates for the other reference frame, it's still the same vector, you're just writing it using the different coordinate system. Okay, so the reason why that may be important is that you have other vectors in this equation as well. You could write any one of these vectors using either the little xyz coordinate system or the capital XYZ coordinate system, but you can't really add the vectors together if they're being expressed in different coordinate systems. You could, but you'd have to figure out how the little I hat and the capital I hat are related in order to do that. So all of these vectors should be expressed in the same coordinate system. Remember that any vector equation that you have, you could draw a vector diagram like this. Vector diagram is illustrating this equation. You could draw a vector diagram to illustrate this. This is similar to what we did in projectile motion. And you could even analyze this equation using the diagram that you draw and maybe avoid writing the vectors down in component form. But we're not going to do that. We are going to write them down in component form. So if you look at the example problem, which this is on page 395, they tell you here it's going to be simpler in this problem to express the vectors in terms of the little I hat, j hat component vectors, rather than the capital I, j, k components. So you're going to take all of your vectors in this equation and either write them with the little I hat, j hat, k hat, or with the capital I, j, k hat. So this is measured by an observer in the rotating reference frame, but you can write the vector down using either coordinate system. Okay, so that's just the velocity. Let's go through all the different pieces that we have in this equation. So we have the velocity of B. This is like if you have someone looking down with a bird's eye view at the problem here, this is what they would say is the velocity of point B. Similarly here, VA, that's the absolute velocity of A. So this is like someone looking down at the problem from the sky would say this is the velocity of B and this is the velocity of A. Then we put you at the origin here at point A. You're rotating with the coordinate system, and you would say this is the velocity of B with respect to A. So this would be like you on the merry-go-round, or you could say like if you're driving in the car, everything in the car, if it's not moving relative to the car, would be at rest relative to you, so then this would be 0. But if you have something moving around inside the car, then it would have a velocity with respect to you. So this depends on how the object is moving within the rotating reference frame. So put yourself as an observer at the base point, rotating with the reference frame, and this is how B is moving relative to you. Then we have the angular velocity of the reference frame as measured by the capital XYZ reference frame. So that's what we have here. So this is like if your merry-go-round is rotating, this is the and the XYZ coordinate system is for the rotating merry-go-round. That would be the angular velocity of the merry-go-round. And then you cross it with the position vector here. This is position of B with respect to A to get the velocity. Okay, so that's just the velocity equation. It gets even more complicated when we look at the acceleration. So this is on page 392 through 393. And I want you to read through this on your own, and we have the derivation here giving us equation 1629. Now this equation is kind of similar to the velocity equation which we just looked at. If you're looking down at what's going on with a bird's eye view, you have the acceleration of point B and the acceleration of point A. And if you're an observer in the rotating reference frame, rotating with the reference frame, you would measure the velocity of point B and the acceleration of point B. So this is not including like how the merry-go-round itself is rotating. This is just how B is moving relative to the rotating coordinate system. So we have the relative velocity and the relative acceleration. And then we have a few other terms as well. Now, maybe it would be helpful to compare this to what we had in equation 1618. So we looked at equation 1626, and this angular velocity is the angular velocity of the coordinate system. But back in equation 1616, when we were talking about a rigid body, we had a lowercase omega for the rigid body, and you could choose your coordinate system so that the angular velocity that you have here is the same as the angular velocity of the rigid body. So for instance, if you're talking about a merry-go-round, you could say that the coordinate system here is rotating with the merry-go-round, and then your angular velocity here would be the same as the angular velocity of the merry-go-round. So you could choose it that way. So then going back to equation 1629, let's compare this to equation 1618. So we have angular acceleration of B, angular acceleration of A. We have angular acceleration of B, angular acceleration of A here. Then capital omega dot. And if I choose my coordinate system so that capital omega is the same as lowercase omega, then capital omega dot would be the same as the angular acceleration that I have here. So this cross product is related to this cross product here. Then I have omega crossed with RBA. That would be what I have here. So if you go back to where they derived 1618, the omega squared here came from the cross product of omega with omega and then crossed with RBA. That gave us this here. Okay, so then we have two new terms in our equation. We have the 2 times omega crossed with the relative velocity plus the relative acceleration. Now on page 393, they go through each piece in this equation. So we talked about this is the absolute acceleration. This is like the bird's eye view. And this is this cross product here, which we had before in equation 1618 as the angular acceleration crossed with RBA. This is the angular acceleration caused by the rotation of the frame. This is the angular velocity effect caused by rotation of the frame. So we had both of these terms before, which were caused by the rotation of the rigid body. Now we have two new terms. So we have the 2 times omega crossed with the relative velocity. This is the combined effect of B moving relative to the lowercase xyz coordinates and the rotation of the lowercase xyz rotating frame. And then we have this new term, which is from the relative acceleration. So both of these are coming now because the distance between point B and point A is changing. So again, if point B is somewhere on the merry-go-round, or let's say a person on the merry-go-round, if that person isn't moving relative to the merry-go-round, then this term and this term are going to be 0, and then 1629 becomes the same as equation 1618. Okay, so we're going to look once again at the relationship between the equations that we just derived and the ones that we had previously, so 1616 and 1618, and then we're going to go all the way back to equation 1610 and equation 1614 to see how the equations in this chapter are all related to each other. So we're going to look at the equations for velocity first. So these equations are all coming from your equation sheet. And we have equation 1626 to find the velocity of point B, which can be a point, let's say, in a rotating coordinate system, but it can be moving relative to that coordinate system. So we have the velocity of A, which is the base point. Then we have the angular velocity of the rotating coordinate system crossed with the position vector here. And then we have, if point B is moving relative to the coordinate system, we have this relative velocity here. But if point B is not moving relative to the coordinate system, then this velocity is 0, and we get equation 1616. This angular velocity is the angular velocity of the lowercase xyz reference frame measured from the capital XYZ reference frame. And in equation 1616, we had angular velocity of the body, and we could choose our coordinate system so that the lowercase omega and the capital omega are the same. So that brings us to equation 1616. Now, if your base point A is not moving, so let's go back to our diagram here. So if A is at rest, so if this is a merry-go-round at the playground, the center of the merry-go-round isn't going anywhere, then the velocity of A is equal to 0, and that gets us equation 1610. Similarly, we got equation 1629, which we just derived for the acceleration of B. We have all these different terms in the equation. If point B isn't moving within the coordinate system, the rotating coordinate system, so if you have a person on your merry-go-round who's just standing on the merry-go-round, then this and this are equal to 0. That gets us equation 1618, where once again, you have to take the angular velocity and the angular acceleration and now make them angular velocity of the body and angular acceleration of the body, but you can define your coordinate system so that that is true. And then we get equation 1618. And if the base point A isn't accelerating anywhere, so if, like, the center of your merry-go-round is not moving at all, so, you know, just at rest relative to the ground, then the acceleration of point A is 0. So the merry-go-round is rotating, but the whole merry-go-round, like the center of the merry-go-round, isn't moving through space. Then that gives us equation 1614. Okay, so really, if you wanted to stick always with equations 1626 and 1629, you could use them in cases where we have been using 1610 and 1616 and 1614 and 1618, but a lot of the terms in those equations would become 0. Okay, so before we finish, some of the terms in our acceleration equation have special names. So this term here is the transverse acceleration. This term here is the centripetal acceleration, and this term here is the Coriolis acceleration. And you can read it. It's named after the French engineer Coriolis. And these three accelerations have associated forces. So remember, Newton's second law says the net force is equal to the mass times the acceleration. Now, if you're looking at the situation with a bird's eye view, then you don't need to take into account these accelerations. But let's say you're in the car and your car's turning the corner, so something on your front seat is moving. So you're in a non-inertial reference frame because your car's accelerating. So if you want to analyze the situation from your non-inertial reference frame, then you have to take these three different terms into account. So I'm going to put some links in the description for this video, and you can read more about the centripetal acceleration and the Coriolis acceleration by following those links. And there's also going to be a video that you can get to from the links in the description, which illustrates the Coriolis acceleration. So if you're trying to walk around on a merry-go-round, you're going to feel a force which is related to the Coriolis acceleration. So if you know of any playgrounds that you can get to that still have merry-go-rounds, you can go walk around on a merry-go-round and experience this, or you can watch the video in the links. Okay, so these are related to forces which you have to take into account only if you're trying to analyze a situation from a non-inertial reference frame. So in Physics 161, we never did that. We always used an inertial reference frame when we applied Newton's second law. But you probably talked about in Physics 161 how if you're in a non-inertial reference frame, it looks like Newton's second law doesn't hold, because if, for instance, you're driving your car around a turn, your car is accelerating, you can have things on your front seat which are moving, and it looks like Newton's second law isn't true, but that's only because you're in an accelerating reference frame. And if you're looking at the situation with an observer standing on the ground, or looking at it from a bird's eye view, you would see that Newton's second law is actually true. Okay, so that concludes our very long introduction to section 16.8. So we have two new equations which we can use, and there are some links in the description for you to explore on your own.